Yeah, lots of people left after the last talk, which did wonders for my confidence. So hopefully everybody here... Thank you. I'm sure they will all miss out, and they will all be very disappointed. Thank you for the introduction. I'm going to talk about Triplestores and SPARQL. I should... Where's the screen? Cool. I'm from EVCC Edinburgh. So, in the next half an hour or so, I'm going to have a very, very quick overview of the introductory material about Triplestores and what SPARQL is and stuff like that. I'm going to have some practical examples and some limitations and caveats, but also pros of the technology, hopefully, and will convince you that it's quite useful in some situations. And the caveat, is that keep going to do that? And the caveat here is that this is basically 4 MSc lectures that I give that I've had to compress into a 25-minute slot. So it will be a very, very, very quick run-through of all the stuff. Immediate caveat is that RDF and Triplestores and query language associated with them are still quite niche technologies, despite having been around since the early 90s. So, as a show of hands, I'm going to make this interactive. How many people have heard or have knowingly used a Triplestore or SPARQL? Oh, wow. That's a lot more than I was expecting. In that case, this might not be quite as introductory as you were hoping. I was kind of aiming at people who've never heard of it. Who has never heard of even heard of RDF or Triplestores? Almost the rest of you. So I've almost got a kind of complete binomial split of never even having heard and have used it. So this will be interesting. So some domains, as many of you know, do use Triplestores in anger, specifically some of the environmental sciences and some of the biological sciences. But hopefully, what I might show is that data modeling is useful and interesting, and the process of building up queries is also useful and interesting to many of you. So, start with some of the kind of theoretical background. So, semantic data is defined as, or kind of metadata is data about data. Hopefully, that's not new for many people. And we can split that into things like system metadata, which is things like file ownership, and modification date, so stuff about the files we see. And then we can have the content metadata, which we might also call structural metadata, or some domains will call it a data dictionary, which is like the who, what, where, when, how data was collected, and things like that. And then if we think about semantics of metadata and data, then we can get into the meaning of data. And so, does a date in a file description mean the date that the data describes, or is it the date that the data was stored, or was it when it was collected, or was it something to do with an average over the day, or the beginning of the day, or things like that? And without accurate metadata, that becomes quite difficult to tease out. And concepts might have specific meanings in different contexts, or they might have analogies, or they might mean the same thing. So, if we say rain, would we also include sleet, or snow, or hail, or would they be described as different words? So, are they synonyms, or are they not synonyms? And again, vocabularies can help with things like that. And if we have semantic data, then understanding what the data means is important, hopefully in just about all areas of research. So RDF is a resource description framework. It's a data model, and it's a way of modeling data. So we can encode information as triples, and triples have 3 bits to them, as their name might suggest. So we have a subject, a predicate, and an object. So in this example, we've got a subject with the cat, and a predicate we can think of as a verb, which is sat on, and the object will be the mat. And it might not be obvious now, but hopefully by the end of the talk it will be, that we can describe almost all data in triples in some form. So, technically, from a semantic data point of view, the subject should be either a resource with the URI, where we see URI, we can normally say URL. There's a slight, again, semantic difference there, but we can ignore that for now. Or it can be a blank node, which refers to something else internally in the triple store. The predicate, so that thing that's a verb in the middle, should always be a resource with the URI, because then we can define it to be something external, and the point about semantic metadata, semantic data, is that we should be able to link things to external places, which will become obviously again in a few minutes. And the object, again, could be a resource with the URI to refer to something externally, or it could be a blank node to refer to another subject, or it could be a literal data type, so it could be a string, or a integer or floating point number or something else, which can be described in a literal format. So an RDF triples can be drawn as a graph mathematically. So a subject or an object are nodes, and then predicates are edges. So I'm not a mathematician, but this is what my mathematician friends tell me. And then triples can be stored in a triple store, which for those mathematically minded people, you can think of as a form of a graph database. And because they are a form of graph database, some very clever pure computer scientists have shown that they can be indexed and optimized and things like that, and their performance can be improved. And so an example of an RDF graph, has this got a laser pointer? So it has. So we can take something that represents the city of Edinburgh, and we can take something that is in the city of Edinburgh, which is the University of Edinburgh, and we can say the university is in the city of Edinburgh. And we can also say that Scotland is the capital of Edinburgh. So, just to annotate that a bit, we can say that in both of these cases, Edinburgh is the object, Scotland and the University of Edinburgh are both subjects, and then this city and this capital are both predicates. And what that means is that we can do some inference, and we can use this graph database to show that the University of Edinburgh is in Scotland because of the links between the data. And that's something that is the kind of the power of RDF more so than relational databases. So RDF can be represented in lots of different ways. So it can be described in XML. So RDF XML is just one serialization format. I won't drill on that too much, but there are lots of other serialization forms as well. So the most common one is TTL, we refer to as Turtle. And the BBC make a lot of their data available through TTL files. So you can go to that website, that URL, and you can see the representation of this first line, which is HTML, and this second line is Turtle, because they do something called content negotiation, which means that when you specify a different file format, it returns the data in a different format. And then we've got, there are different forms as well, so N-triples and N-quads and JSON and things like that, which are not important at the moment. And then, finally, we come on to this thing called vocabularies. So a controlled vocabulary is a means to describe the semantics of data, and it is a way of describing precise definitions for lots of terms, and it can be used for the metadata or for the data itself. We'll see some proper examples in a few minutes. And ontologies, so there's a weird difference between, again, a semantic difference between the term vocabulary and the term ontology. So an ontology tends to be a bit more, have semantic meaning, whereas a controlled vocabulary is normally just a list of terms. And ontologies themselves are written in a language described itself in RDF. So it becomes this kind of weird, kind of circular, very, very meta way of building a language. That gets very, very complicated very quickly, and it would be a whole multiple credit master's module rather than a 25-minute talk. So again, I'll skip over that. So there are lots of real-life triple stores, and some of these we're going to see in a minute. So DBpedia is an extraction of structured content from Wikipedia. So it's not all the page content, but it's so things like on Wikipedia, where you get content boxes and things like that, things that are structured, we can get that. Wikidata is also a representation of most of the Wikimedia family stuff. So that includes not just Wikipedia, but the data behind it as well, which is also public. I'll also show you in a few minutes the NERC vocab service. So that is a proper controlled vocabulary of hierarchically organised vocabularies aimed at the environmental sciences. I've a bit of a soft spot for that, given I helped build it quite a long time ago. And then both the UK and Scottish governments, and probably the Welsh government, but I haven't checked, have got quite a lot of open data that's geographically labelled. So we will see one of those as well. Are there gremlins around here somewhere? So SPARQL is the query language for RDF, and it's what SQL is to relational databases. It is a W3 standard, so it is kind of well defined. And just for a very, very quick intro, if we've got 4 triples where we have 2 subjects, so T1 is somebody called Chris Wood, based at Edinburgh, and T2 is Barack Obama, based at Washington, then we can write a SPARQL query that looks a bit like that. So it looks a bit like SQL, so we can select name. So variables in SPARQL are prefixed by a question mark, and then we have a where clause. So we're looking for something with a name and want to find the name, and here we will get back Chris Wood and Barack Obama because we're looking for the things that are called fo of name. So now that I've gone through the boring theory, practical stuff, this is going to be a bit more like carpentry style. So if you want to follow along, feel free. The code queries are on a gist page that I set up about half an hour ago. So that link isn't on the set of slides. It's uploaded to the conference folder. But I will also have it all online on the screen. So if you just want to watch, you can do that. Give people a second to go to that website if they want. So, one thing to find out that the things that a triple store describes is this fairly complicated looking query, but actually it's about the most simple thing that we can get. So we want to find all of the things that is in the triple store, basically all the predicates. So A is actually a shorthand in the language for things that are of an RDF type. An RDF type is the standard way of describing what predicates exist, and we can look for the concepts of those. So I am going to do this live, and hopefully it's all going to work. This is where I can't work out what screen is on. Where? So there were 4 screens in front of me, and it's quite hard to work out which one is going to end up where. So, and so we're going to take each of these in order. technology works. So the first query is going to be this one, which is the one I've just shown on the PowerPoint. So let's copy and paste that into the DBpedia endpoint and execute it. And what that's going to show is basically all the predicates that exist in DBpedia in not any kind of functional order or anything. So we can see that DBpedia describes things like people and activity and names and actors and things like that. And we can scroll down that list and we can see that there will be lots of them and it will be paginated. And that has only listed the first 100 because we've limited it to 100. Gists aren't stored in the order I wanted them to be. So then we can look at the things which are only to do with Edinburgh. So if we copy and paste my second example. So here we are specifying that Edinburgh is a subject, and we're going to look for all the predicates and all the objects to do with Edinburgh. And we've got things which are of RDF type. We can see that it's a place and it's a location and it's a city and things like that. And we can go down, and again, there are lots of them. And we can go down, and there are lots and lots and lots and lots of things. So we might want to see how many of them there are. We can go back, and we can do a count. And there were 1,649, so that's the number of things that DBpedia has about, or the number of predicates that DBpedia has about Edinburgh. And we can find the distinct ones, and we can order them. So order in SPARQL is a bit like order in SQL. So it will be it will do alphabetical by default. So these are the things. We can see that there's now only one representation of each of these, whereas before there were multiple ones for RDF type and things. And we've ordered them alphabetically. So the first thing is the total area of Edinburgh and the urban area, and then population density and things like that. So my fourth query is to only find, this is where it starts getting a little bit complicated, and we can see what predicates exist for Edinburgh that are only from the DBpedia ontology. So we're not going to look for any of the other external ontologies, and we're just going to start with dbpedia.org as a string filter. And again, this will actually be similar to the previous example because a lot of the other ones are further down the alphabetical list. But that's just a way of kind of showing that we can do a string filter on the things that we are querying. And we can also then start to think about getting individual bits of data out. So we can look at the abstracts. So an abstract in the DBpedia world is basically the description of it. And we've got lots of descriptions here, and they're all in different languages. And one of the advantages of RDF is that we can represent natural languages easily, and you will see at the end of each of these strings there is an @ symbol and a 2-letter ISO language code, and that is a language. So the first line there is Arabic, and the second line is, I can't remember, French Canadian, I guess. And because we've got that built into the data, we can extract only ones that are in, for example, Spanish. So if I go back to my query, and we can use this filter keyword to extract languages that are in Spanish. So if I run that, then I get 2 results. And if we go to the end of the line, we'll see that there will be a @ symbol for ES. I'm probably not going to get through all my examples. I kind of wrote too many examples. I knew I was going to have too many to do. That's why I put them on gist, so we can go and look at them in your own time if I run out in a few minutes. We'll continue anyway. My next point is that technology isn't the problem, people are, which is a phrase that I've been taught and is quite good. So if we look at the next one, this is where data modeling goes a little bit wrong. So here, this has been labelled as being in English, but I would say that Old Wiki, which is one of the nicknames for Edinburgh, is not English. It's Scots language, and that also has an ISO code. So the modelling here is that the language code has been applied incorrectly. And that is also the case for my next example, which I won't do. That's been listed as being English, despite being a Latin phrase. And then let's start doing some utterly more complicated things, just to show you the power. So here we are looking for start routes, things that start in Edinburgh that are of type road. So we've got these examples here. So these are the things that Wikipedia knows about that are of type road, and they have a start place of Edinburgh. How long have I got left? A minute. Cool, great. So how many of these can I get through just to show you how some of the more exciting things. So I'll just talk through some of these then. So example 10 here, we can remove roads, so that will only return things that are of type railway in this case. We can do some weird grouping, so this is doing an aggregation, so we are summing together all of the river lengths in England, Wales and Scotland, and that's only going to return 3 results, so it's going to return the total length of rivers in England, the total length of rivers in Scotland, the total length of rivers in Wales. We can look at, there's quite a lot of drug information in Wikipedia, so this one is using an OR statement, kind of an in statement to optimize ORs, so we can, that works the same way as SQ as well. And you can see as we kind of go down here, we can start doing some really complicated things. So here we've got a multiple nested select, and we're doing a group concat is a way of concatenating strings from a one-to-many relationship. And I think I'm being told that that is it. I did have a couple of closing slides, which I will, which I can't find my mouse now. These are all the examples. So, if this is residue appetite, I would guess there's content negotiation, and come and speak to me. And if you want to implement them, make sure your data is well structured, and don't forget, technology isn't a problem, humans are, and following standards is advantageous, and it improves fairness of data, and that's where the link to Neil's thing comes in, and it's a niche technology, and there can be lots of errors. Sorry.
Thank you, Chris. That was really nice. Yeah, I really liked how you set up the examples as well. I think I'm going to try this out later. Okay, so we have 2 questions for you. Okay, the first question. Are Triplestores and, you called it SPARQL, I called it SPARQL, which was wrong, used for medical data, like patient data or scientific research data?
Yes. So more so for scientific research data. So I know that EMBL, the European European Molecular Biology Lab, uses SPARQL in anger and stores lots of data and metadata in their vocabs. I also had the example about the NERC vocab server. So that's a controlled vocabulary of metadata rather than data.
Okay, next question. Or is it more of a comment? Sorry, that was a bad joke. Great talk, Chris. I'm a lazy RSEs. Okay. Do you have a feel for how good large language models have got at writing these SPARQL queries?
Kind of. I did try asking ChatGPT to write a simple example a couple of years ago, and it did do quite a good job for simple queries. I haven't done it for anything massively complicated. I guess the problem is, and I kind of, I had to skip over that at the end, but you have to understand the data and the modelling, how the data being modelled to write queries well. So I would imagine that even the best LLMs haven't managed to ingest all of the triple stores to work out how the data is modelled to know which predicates to use when.
Okay, and the next question. At the beginning of your talk, you mentioned SPARQL is quite niche. What do you think are good ways to help users start using SPARQL?
So there are some decent tutorials online. That's kind of how I learnt. And find examples. So I guess when I was putting this talk together, I wanted to find some interesting examples that I will leave online, obviously, for as long as GitHub exists. So feel free to go and use them and abuse them and edit them and work out how they work. Yeah, feel free to get in contact with me. I wouldn't say I'm a particular expert. There are lots of other people in here who say they've used Triplestores as well, who have probably got different experiences. But yeah, find examples and work out, go and find some simple examples and just build up on them. And I think DPpedia, despite its some of the problems of how the data has been modelled, is a really good resource because it's got all that information there. And it's quite easy, for things that we know things about, like I do the Edinburgh example because people understand that it's a place and it's got a name and it's got descriptions in different languages, and building upon that kind of example.
Okay, and the next question. One of the advantages of RDF is that it allows machines to reason about things. Given that LLMs are good at spotting unusual things, is it likely that combining the two will allow them to identify incorrect metadata?
That's interesting.
It's a very long question.
No, but it's a really interesting thought. Potentially, but again, I would probably come back to data modelling, or incorrect data modelling is a human problem, and could an LLM, like in my example of the nickname of Edinburgh being in the wrong language, could an LLM spot that? Probably, maybe. I don't know enough about Gen AI really to know how easy that would be to do. I would say yes, with the caveat of, because we think that Gen AI can probably do almost everything, but I don't know actually how easy it would be. But yeah, maybe somebody should try that. Maybe that can be an MSc project for next year for somebody.
There you go, you have a project. Okay, those are really good questions. I don't think we have any more, so this will conclude the session. And now we have lunch. Thanks, everybody, and thanks to the speakers again. Thank you, Chris.